Hi budding engineers, welcome to Section-Fink lectures and welcome to the new playlist on the design of steel structures. We are discussing the analysis and design of roof trusses, wherein in today's class we shall see the designs of the struts, these struts as well as the main sling, this part as well as the minor slings, right? As per the limit state method IS 800 2007. In the previous class we have seen the design of this top card member, which is called the principal rafter or common rafter, and the bottom card member, which is the principal type, along with the bolted connections. I hope you enjoyed the discussions there. Then don't forget to click like, share, subscribe to our YouTube channel and turn on all the notifications for our YouTube channel. Right now, let us see the brief profile of the speaker. That is I, Dr. D. Rupesh Kumar, obtained my BTech in Civil Engineering from Nagarjuna University in 1994 and MTech Section Engineering from JNTU Hyderabad in 2000 and PhD Section Engineering from JNTU Hyderabad in 2009. Presently, I am working as Professor of Department of Civil Engineering, University College of Engineering, Osman University, Hyderabad, Telangana State. Right? I have an experience of 27 years, of which 7 years is in industry, 20 years is in teaching and research at graduate and postgraduate levels. My research areas include reinforced cement concrete design, steel structural design, structural analysis, part element analysis, earthquake engineering, bridge engineering, structural optimization. I published 45 research papers in international as well as national journals and conferences, organized 3 international conferences and 11 national conferences and workshops, attended 43 workshops, visited 2 countries, delivered 13 guest lectures and edited 3 books, supervising 14 PhD scholars and supervised 30 MD theses. I am actively involved in various consultancy works that are offered by the department and completed over 770 plus design proof checks as well as 150 plus designs of the reinforced concrete, steel, composite, low-rise, high-rise, multi-story buildings and road as well as rail bridges. Now, once we see this, let us move to the discussion student. Right now in today's class we shall see the design of these struts as well as the main sling as well as this minor sling along with the bolted connections, right? However, in the previous class we have seen the analysis of this Fink or French roof truss, wherein the span was 16 meter and the height of the truss was 4 meter. We have fixed the geometry and even we have analyzed, we got the dead load, live load and wind load, and later on we have analyzed the loads and we got the design forces in the load combinations, and even we have designed the top chord member as well as the bottom chord member. Therefore, now we will see the design of this main sling and that of the minor sling as well as that of these struts along with the bolted connections, let me go back to the design student, right? Therefore, now I wish to design the struts. Therefore, this is how the analysis what we have done in the previous class, right? These are the struts wherein these are U1, L1, right? U2, L2, so on and so forth, U7, L4, right? Wherein the forces, all these are the compression forces are represented by minus, right? Therefore, out of all these, now we can see that minus 35.4 is the maximum value. Therefore, that is my design compression force in 1.5 dead load and live load combination, as well as even we can say nowhere I have minus that much value. Therefore, that is a design compression force even where the maximum positive value is there. Now if I check, now I can see that I have a maximum plus value as 37.8 is the design tension in 1.5 dead load plus wind load combination. Here plus indicates tension and minus indicates compression. Please make a note. Therefore, I'm just recalling these design forces. Right? Even similarly, we have analyzed the minor sling as well as the main slings also. We got the design forces in minor sling as 19.95 tension and 22.5 as compression. Right? Even for main sling, I got 58.05 kilonewton as tension and 64.05 as compression. Right? Once we examine this, the design forces, let me move to the designs. Right now, let me start the design student. Right? Therefore, we are there in the design of the strut, wherein just now I am initiating this design, wherein just now we have seen what is the design compression force is 35.4 kilonewton as well as the design tension force is 37.8 kilonewton, right? Wherein wherein here you please see that here the design forces are so small, right? Therefore generally we'll be using one angle connected to one side of a gusset plate, like this, one angle connected to one side of a gusset plate, whereas the top chord member and bottom chord members were designed using two angles back to back connected to 12 thick gusset plate, right? There is a top chord member, even the bottom chord member was designed like this, right? Now I don't require two angles back to back, just one single angle is sufficient. Therefore now even the other day I fix the geometry, therefore what now I'll do is I'll design for compression first, later on I'll check for tension. And even from the geometry we know that length of the strut U2L2 is sort of 5 square minus 4.47 whole square, right? Where that works out say 2.24 meter or say 2240 mm is the length of this strut, right? Or let me show this strut, right? Now this strut is like this, right? And this is that strut what we have, right? Or let me go back, right? This is that strut, or let me go back to once again the same schematic what I have just shown, right? This is that strut, student, right? Therefore this length is that much, right? Whereas these struts are smaller length, this is a bigger length. Therefore obviously this will be designed. Once this is designed, I think the same section can be put for even these small struts. Therefore I'm designing this member strut, right? Where now I do have the length, that length is equal to 2.24 meters. Now however the design compression force is not that large, therefore I am assuming a medium slenderness ratio, lambda is equal to 150. The other day you please see that for top chord member or rafter I have assumed lambda is equal to 100, whereas for the bottom chord member, because that length is 6 meter, there I assumed slenderness ratio as 200. Now because here the single angle is there along with the 2.24 meter length, as well as the compression force is also small, therefore I am assuming a medium slenderness ratio, lambda is equal to 150. Therefore now from table 9C, page number 42 of IAS 800 2007, let me just go to that IAS 800 2007, student, right? Page number 42 for lambda is equal to 150 and Fy is equal to 250. Yes, now I do have this design compressive stress FCD in MPa 58.8. Therefore I'm just noting down that value. Sorry, I'm for lambda is equal to 150. I'm noting down that value as 59.2 for lambda is equal to 150, and Fy yield stress of the steel is equal to 250. It is 59.2. Therefore once I note down that, now I'll get towards the area of the cross-sectional area required for this angle, right? Therefore area is equal to compression force divided by permissible design compressive stress, which is 35.4 into 10⁻³ divided by 59.2, or it works out around 598 mm square. However, you increase this area by 25 to 50%. Therefore now let's say that I am proposing to start with a gross area of 25% more. Therefore 1.25 multiplied by 598, I'll get 748. Therefore if I go to Structural Engineering Handbook 1, right, or the special publications 6/1/1967, as per the Indian standard side, if I go to this table 3, page number 8, you go to that table 3, page number 8, student, wherein I'll try to choose a single angle section ISA 55 by 8, wherein for such section you can see that with 8 mm it furnishes an area of 818 mm square, right? 818 mm square. Therefore it is okay. Once it is okay, then what now I will note down is what is the radius of variation. Therefore now I will note down that in the next, right? Therefore I do have ISA 55 by 55 by 8. Therefore accordingly I will note down the radius of variation RXX and RYY values, which are respectively these values. Therefore I am noting down those values 1.64 and 2.07 also respectively, right? Therefore, I've just noted down that area which is much greater than that required area of 748, even that is with increment of 25%, right? Therefore, it is okay from that area point of view. R min, just now we have seen that R min is equal to now RVV, which is 10.6 mm, 10.6 mm, and even what is now B1 and B2, because these are even. Now you can see that this is an equal angle section. Therefore, the outstanding leg itself is 55, as well as the connected leg itself is 55. Therefore, this is B1 as well as B2. Both are 55 mm, and thickness is equal to 8 mm. And the stress ratio epsilon is equal to square root of 250 divided by Fi, where Fi steel, for the steel is 250. Therefore, the stress ratio is equal to 1. Now, assuming the strut to be connected by more than one bolt, this is my assumption, may differ also. Therefore, the effective length K is equal to say 1L, right? The effective length factor is equal to 1. Hence, now I'll get to say 2240 mm. Now, if I go to class 7.5.1.2 of IS 800 2000, page number 48. Let me go to that page number 48, student, right? Page number 48 of IS 800, right? Page number 48. Yes. And then in page number 48, student, right? Now we can see that loaded through one leg only, Therefore, in such a case, right, the flexural torsional buckling strength of single angle loaded in compression through one of its leg may be evaluated using the equivalent slenderness ratio lambda E, given by this square root of K1 plus K2 multiplied by lambda V square plus K1 multiplied by lambda psi whole square, where K1, K2, K3 are the constant depending upon the end conditions as given in the table 12 that we'll see here, right? And where lambda VV is the is L by RVV, the actual slenderness ratio about this VV axis, that would be epsilon multiplied by square root of pi square epsilon, sorry, not epsilon, pi square multiplied by E. There's a typographical error, pi square multiplied by E divided by 250, as well as lambda psi is equal to B1 plus B2 divided by 2T, that divided by epsilon multiplied by pi square E divided by 250, where L is the center to center distance of the supporting member and RVV is the radius of gyration of the about minor axis, and B1, B2 are the width of the two legs, and T is the thickness of the leg, and epsilon is the yield stress ratio 250 divided by square root of Fi, that just now we have obtained, right? Whereas this is a table showing the constants K1, K2, K3, K1, K2, K3. Now let us see the calculation, student, right? Therefore, now I'm just noting down that lambda VV, this formula wherein I'm substituting L is equal to 2240 divided by RVV is equal to 10.6 divided by stress ratio, yield stress ratio is 1 under root pi square Young's modulus of the steel is equal to 2 into 10 to the power 5 divided by 250. It works out, say, the value 2.3782 up to fourth decimal, right? Lambda psi is B1 plus B2, right? This B1 plus B2 means B1, B2 both are 55 divided by 2 times 8 mm thickness divided by 1 multiplied by pi square multiplied by 2 into 10 to the power 5 divided by 250. It works out, say, 0.0777, right? 77, right? That is how. Now we already made an assumption that I will be assuming more than one number of bolts. Therefore, assuming two number of bolts. Let us say if I assume two number of bolts and assuming it to be fixed condition. Therefore, I will be maintaining, right, at regular intervals, right. I will be tightening the bolts at regular intervals so as to maintain that as a fixed condition, right. Therefore, my fixity is fixed. Therefore, from this table 12 of page number 48, right. Now I have these coefficients, right. Now let us see these coefficients, right. Yes, right. Therefore, the number of bolts from table 12, number of bolts greater than or equal to 2, I am assuming fixed. Therefore, this first row K1 is equal to 0.2 and K2 is equal to 0.35 and K3 is equal to 20. Therefore, I am just recalling those. I have just noted down here. I'll be substituting into this equivalent slenderness ratio formula. Lambda is equal to, right, K1, where K1 is equal to now under root 0.2, K2 is equal to 0.35 multiplied by this lambda we just now we got 2.3782 whole square plus K3 is 20 multiplied by 0.077 whole square. It works out, say, 1.517 is the effect equivalent slenderness ratio. Please make a note. This is equivalent slenderness ratio, not actual slenderness ratio. However, from table 7 of page number 35. Now let me go to that page number 35, student, of IS 800, right? Now page 35. Therefore this is page 35 is like this, right? Wherein I do have, yes, the buckling class. The buckling class is C class. The buckling class is C class. Therefore now what I'll do is, for this buckling class, the imperfection factor is 0.49. Let me see that imperfection factor, right? Therefore from this table for buckling class C, because single angle is under buckling class C as per this table, right? As per this table, right? Therefore for that buckling class C, now the imperfection factor alpha is equal to 0.49. Once I note down that imperfection factor as a 0.49, student, then what I'll do is, even from class 7.1.2.1, page number 34, now I do have this pi given by this just now. Let me go back to that page number 34, wherein I do have, right, this design compressive strength PD is equal to P should be less than or equal to PD, where PD is equal to AE FCD, right, where AE is effective sectional area and FCD is a design compressive stress as per this IS 800 2007 class section 7 class 7.1, right, where FCD is a design compressive stress. FCD is Fy divided by gamma m naught divided by pi plus square root of pi square minus lambda square, or that is given by x multiplied by Fy divided by gamma m naught, where x is the stress reduction factor, or it should be less than or equal to Fy divided by gamma m naught, where pi is equal to 0.5 multiplied by 1 plus alpha multiplied by lambda minus 0.2 plus lambda whole square, where lambda is equal to non-dimensional effective strength ratio given by square root of Fy divided by FCC, that is square root of Fy multiplied by KL by R whole square divided by pi square E, where FCC is the Euler's buckling stress given by pi square E divided by lambda whole square, where lambda is equal to KL by R whole square. Even this stress reduction factor is given by 1 divided by square root, divided by pi plus square root of pi square minus lambda square, right? That is how. Now I'll calculate this pi value. Therefore that pi, if I substitute, now I'll get 0.5 multiplied by 1 plus alpha is equal to 0.49, and lambda E effective strength ratio is equal to 1.517 minus 0.2 plus 1.517 whole square. It now works out, say, 1.973. Therefore the design compressive stress given by this formula, now I am substituting into this formula, Fy is equal to 250 divided by gamma m naught is 1.1, because the partial safety factor when governed by the yield stress, gamma m naught is equal to 1.1. Even the other day we have seen in the given data, pi is equal to 1.973 plus square root of 1.973 whole square minus 1.517 whole square. It now works out, say, 90.26 MPa, Newton per mole square. Therefore from table 2 of page 18 and even from figure 9, that figure 2 of page number 19. Let me go back to that page 18 and 19 respectively, student, of IS 800. Page number 18. Yes. Therefore now whether means we are now checking what is the buckling class, right? What is the section classification? Therefore now I would have the angle section. Therefore this is how it is defined as B, and this is defined as D, and this is a T for single angles as per this figure 2 dimensions of the section. Even B1, BE are also given. Therefore for different sections these are defined. Therefore now I'll calculate for my section. I do have B is equal to D, both are same because both are 50.55 respectively, and thickness is equal to 8 mm. Therefore now I'll see what is the section classification. B by T and D by T both are 55 by 8, which is 6.87. Now let me go back to this table, wherein what is 6.87 from this section classification of IS 800, student. Therefore single angle connected to this is how the angle compression due to bending, right, or single angle, this one, right, or double angles with components separated, right. Therefore wherein I would have B by D and D by T and B plus D by T, all the three are there. Whereas if I examine that, therefore if this is less than or equal to 15.7, both are 15.7 times epsilon means 15.7, then the section is semi-compact. If this is greater than 15.7, then the section is a slender section, therefore buckling will happen, right? Slender section means I need to reduce the effective area. That we'll see in the next case that may arise, right? And that is okay, therefore that is okay. Once I have calculated that this is less than 15.7, it is okay. Now let me check what is that b plus d divided by t. Therefore that now works out, say actually b by t itself is 6.87, therefore b plus d is 55 plus 50, 110 divided by t, 8. That now works out, say 13.74. It should be less than 25 as per this codal specification, right? Therefore b plus d should be less than 25 times epsilon. Therefore it is okay. Even it is okay in all the three criteria. Therefore effective area need not be reduced. Therefore the design compressive strength PD as per this formula is equal to FCD multiplied by AE. However, FCD just now we got design compressive stress as 70.26 multiplied by 818 divided by 10 to the power 3. It works out, say 57.47 kilonewton, which is greater than 35.4. We have started design to resist 35.4 kilonewton design compression. However, it is resisting 57.47 kilonewton. Therefore it is okay. This is okay. This single angle, I say 55 by 55 by 8 is okay, right? Or if you wish further, you can optimize. You can reduce the section by 55 by 55 by a lesser thickness 6 mm, right? If you want to optimize, right? Now once that is over, now what I'll do is whether is it okay in tension also, whether it can carry this much of tension or not, that of 37.8 kilonewton or not. Now I'll check. Therefore now I'll go to this class 6.2, page number 82, sorry, page number 32, wherein, let me go to that page number 32, student, of II set 100, 32, yes. These are the design of tension member, wherein T should be less than TD, where that is governed by the three criteria. One is under axial, one is the design strength due to the yielding of the cross section TDG, and the second one is rupture strength at the critical section TDN, the third one is block shear TDB. Therefore, let us see the first one. The design strength due to yielding of gross cross section TDG is equal to AG FI divided by gamma m naught, right? Even the second one is design strength due to rupture of the critical section. This is not the plates, this is the angles. Therefore this is given by TDN is equal to 0.9 ANC FU divided by gamma m1 plus beta multiplied by AGO FI divided by gamma m naught, where beta is given by this value 1.4 minus 0.076 W by T FI divided by FU. BS divided by LC should be less than or equal to FU gamma m naught divided by FY gamma m1 should be greater than or equal to 0.7, as well as the third criteria is the design strength due to block shear, wherein bolted connection. Therefore now TDB is first criteria ABGFI divided by root 3 gamma m naught plus 0.9 ATN FU divided by gamma m1, or the second criteria is TDB is equal to 0.9 ABN FU divided by gamma root 3 gamma m1, sorry, root 3 gamma m1 plus ATG FI divided by gamma m naught. Therefore now let us see the using the first criteria, student, the design tensile strength due to yielding of the cross section TDG is AG. AG is nothing but the gross area 818 multiplied by FI 250 divided by 1.1 divided by 10 to the power 3. It works out, say 185.9 kilonewton. However, even how to calculate in the other two criterias, right? That in rupture of the net section as well as the block shear criteria, we have discussed them elaborately in the videos of design of tension members. You may just go through that. However, even I can say they are approximately 70 to 80%. Therefore, even if I assume 80% of that of this TDG, it now works out, say 148.72 kilonewtons, which is much greater than the tension of 37.8 kilonewton. Because I have to have much of the cushion here, I am not checking for this. However, you are advised to calculate the exact values as per the codal specifications. Now you may refer back to our design of tension member videos there, right? Now therefore it is okay in tension also. Therefore this is my final section, because it is passing in not only in the compression as well as also it is passing in tension criteria also. Hence this section is the final section. Hence now we'll go to the bolted connection designs. We have assumed 20 mm dia bolts. Even in the previous class we have assumed the 20 mm dia bolts. Therefore the design strength of these bolts in the single shear, right? Now this is the plate. The plate will, sorry, this angle is connected to one side of a gusset plate. Therefore there is only one single plane at which there can be a shear failure. Therefore the bolts are in single shear. They are in single shear. Therefore the strength of the bolted connection in single shear, it is equal to VD SB is equal to, the other day we have calculated in double shear, right? That worked out 90.52. Therefore that divided by 2, which now works out say 45.26. Or let me show that in double shear, right? This is how we have assumed the diameter of the bolt as 20. Therefore from this table 19 of page number 73, the diameter of the hole is equal to 2 mm extra. Even we have assumed the pitch as per this class 10.2.2, page number 73, pitch should not be less than 2.5 nominal dia, or say 50 mm. And as per this class 10.2.4, page number 74, exit distance should not be less than 1.5 times the diameter of the hole, or say that works out say 33, or say exit distance itself is 33. Therefore the design strength of the bolt in single shear, therefore that is given by this VDSB is equal to NN as per this class 10.3.3, page number 75. NN is equal to 1 now. Only that is the only change. However, this net area of the bolt is equal to 245 multiplied by 400 divided by root 3 multiplied by 1.25 divided by 10 power 3. It now also say, because it is in single shear, 45.26. That is what I am just recalling here. Therefore 45.26 is my design strength in the single shear criteria, whereas the design strength of the bolt in bearing criteria is VDPB is equal to 2.5 kb DTFY. Or let me see this codal specification, right? Let me see this codal specification, student, right? As per this class, let me go back, right? There is a there in this page number 75, right? Let me revisit this page number 75, right? Yes. Therefore this just now we have seen the shear capacity of the bolt SB is equal to Vn SB divided by gamma NB, where Vn SB is equal to Fu divided by root 3 NN A and B. That now just now calculated. I got that result. I got the result as this 45.26. Therefore now I want to calculate that design strength of the bolt in the bearing criteria or bearing capacity of the bolt, which is equal to VDPB is equal to Vn PB divided by gamma MB, where Vn PB is equal to 2.5 kb dt Fu, where kb is the least of these four values: E divided by 3d naught, P divided by 3d naught minus 0.25, Fu divided by Fub divided by Fu, and 1. Therefore out of all these, whichever governs the designs. Or if I see now I would have, even the other day I have calculated this, right? Let us see this. What are these calculations, right? I would have kb. From this, kb is equal to first criteria, P divided by 3d naught 35, sorry, E divided by 3d naught, which is 33 divided by 2, 3 multiplied by 22, which is 0.5. P divided by 3d naught minus 0.25, it works out as 50 divided by 3 multiplied by 22 minus 0.25, which is equal to 0.5. Fub divided by Fu, 400 divided by 410, which is equal to 0.975, and last one is 4. Therefore out of all these, kb is equal to 0.5, right? Even what is the thickness? Thickness is either now single angle thickness is equal to 8 mm, and the gusset plate is assumed as 12 mm thickness. Therefore either 12 mm or 8 mm. Out of these two, whichever is minimum, 8 mm will fail first. Therefore using this, now let me calculate the design strength of the bolt in bearing criteria, which is equal to 2.5 multiplied by 0.5 is the kb, just now we have seen, and the diameter of the bolt, sorry, right, is 20 mm, and thickness of the thickness is the thickness of the angle section only, thickness of the angle section, because the gusset plate is 12 mm, this is 8 mm, this will fail first. That multiplied by 400 divided by 1.25 divided by 10 to the power 3. It works out as 64. Therefore, the bolt value is the least of 1 in shear criteria, the 2 in bearing criteria. Therefore, out of these two, 45.26 and 64, 45.26 is the minimum value. Therefore, the number of bolts required, N req is equal to either compression or tension, whichever is maximum. Therefore, out of these two, now we can see that compression is 35.4 and tension is 37.8. Therefore, tension is maximum. Therefore, I am recalling that as a design force for the calculation of the number of bolts, 37.8 divided by that bolt value 45.26. Our side works out as 0.84, but nevertheless we have already assumed that as fixed. Therefore, at least if I provide two number of bolts, then that will be presumed to be fixed. If I tighten those nuts at regular intervals, like this, then only it is presumed to be fixed. Otherwise, it is hinged. Therefore, hence provide single angle ISA 55 by 55 by 8 mm by 220 mm dia bolts at a pitch of 58 at an edge distance of 33 mm as shown in this figure. Now I will show this figure, student. For this, my ISA 55 by 55 by 8 provided by means of 220 mm dia bolts, both connected leg as well as outstanding leg are 55 mm, and the thickness is 8 mm like this, and thickness of this gusset plate is 12 mm. That is my design. Or even if I show that final design is like this, right? This is how, if I cut a section, right, what I can see is this single angle connected to one side of a gusset plate by means of two number of bolts. Please see, here I am connecting here two as well as two bolts here. Please see this, student, right? Therefore, these are the two number of bolts are being connected to the gusset plate, this gusset plate. Therefore, that is how the design of this strut, which is of more length, right? Even the same section may be adopted for this strut of smaller length, or even that may be optimized. Now, instead of 50 by 50 by 8, even you can say 50 by 50 by 6 may also be okay. That, however, I provide even the same section for these struts also as 50 by 50 by 8 along with two number of bolts as shown in this figure. Therefore, that is all the designs of the struts, right? Once I conclude the designs of the struts, then what I'll do is I'll proceed with the design of minor sling. Right? Now, let me show what is a minor sling, student, right? Then I'll come to the design aspect, right? Therefore, here these components are what referred to as the minor slings, right? This is what referred to as the major sling. Right? This is on the half the symmetry I'm showing, student, right? Half the symmetry of this truss, right? Therefore, this is minor sling, and this is the main sling or main sling or major sling. Therefore, I'll note down the design forces from this table of the analysis. Therefore, for minor sling, therefore now I have to have the maximum compression. Maximum compression as, say, if I examine this, where I do have negative maximum is here 22.5 is my design compression force, as well as where I do have the maximum positive value because that is tension. Therefore, here I do have in member U2 L1 as maximum tension 19.95. Therefore, these are my design forces. I am just recalling these design forces and I am initiating the design now. Right? I am initiating the design. Therefore, now let us initiate the design, student. These are the design forces, right? Of compression 19.95 kilonewton and tension of 22.5 kilonewton. Once I recall these forces, what now I'll do is that now first I'll design for compression, whereas the length, even the other day once we fixed the geometry there I have calculated the length. I'm just recalling this. Therefore, there is nothing but square root of 1.12 because that of the strut, right? Strut plus that of the major panel, right? Panel on the inclined slope direction. Therefore, that is how, right? That now plus 2.235 whole square along this inclined direction. Therefore that now works out, because it is 90 degree, hence I'll get 2.5 meter. 2.5 meter is my length of this minor sling, this one, right? This length, student, right? Therefore now I'm getting this, right? Because this is 1.12 and this is 2.235. Therefore what is this? Because this is 90 degree, therefore it now works out this value, Therefore I calculated that length. Once I calculate this length, even now we can see that there is a small compression as well as even the small tension, right? And for which even I can assume only a single angle connected to one side of a gusset plate only. You don't require two angles for this much of small force, right? Therefore I'll assume only single angle connected to one side of a gusset plate. Therefore even just now I have designed using this ISA in the previous subheading for the strut. If I designed ISA 55 by 55 by 8 with 220 mm bolts, it could able to resist a tension force of 37.8 kilonewton as well as a compression force of 35.4 with that much of almost here and there the same length. Even you can see that the length is also 2.24 meter. Even here I do have for this minor sling also, here and there the length is almost the same. Therefore without much checking I can say the same section may be provided, right? Because this is just subjected to a compression force of 19.95. therefore that can able to resist even approximately 37.8. however, because of this change in length 2.5, even it may reduce by small amount or say approximately 35 kilonewton. However, it is subjected to a compression of roughly 20 kilonewton. Therefore it is okay. Even that tension force, it can resist up to 185.9 in the yielding of the gross cross section. However, it is subjected to only 22.5. therefore it is okay, right? Therefore like that I can say the same section may be provided ISA 55 by 55 by 8 with the 220 mm dia bolts without much calculation. Or if you want to optimize, now what I'll do is, alternatively what I'll do is I'll try with an optimized section. Therefore I'll proceed with ISA 50 by 50 by 8. 50 by 50 by 8. Or let me go to this table, student, right? Means I need to do another do loop, right? Therefore I am there here. Therefore, right, design for compression, right? Assuming this, then ratio I got this area, right? I'll get this area 19 point, this divided by this FCD is equal to this much. Therefore I am assuming from this SP61 page number 8. Therefore if I go to that page number 8, or let me go back to that page number 8, student, right, of SP61. Sorry. Therefore I am there in page number 8. Therefore for ISA 50 by 50 by the section is 50 by 50 by 8, 50 by 50 by 8, for which I would have an area is equal to 479, because here the compression is equal to 19.95, student, 19.95. therefore the area required is very small area required, right? Like this, right? The 19.95, even if I assume the same standard ratio lambda for single angle section, it is 59.2. Therefore you just require 336. Even if I increase this by 25% more, you require an area of 420. Therefore what now I'm doing is I am trying with this section, wherein ISA 50 by 50 by this section. Let me go to that section, student, just bear for a moment. 50 by 50 by 8. Therefore for which now I do have the sectional properties. The sectional properties are like this, right? From this SP61, right? 50 by 50 by 8, right? I'm just noting down these properties, right? 50 by 50 by 8, right? Just wait for a moment, right? I do have, sorry, this is 50 by 50 by 6, student, not 8, right? Where the area is equal to 479, right? You please see that, right? ISA 50 by 50 by 5, where I do have 479. I'll note down the radius of variation, right? Radius of variation, which is Rxx is equal to Ryy and Ruu Rvv. Out of all this, right? Therefore, 0.97 is the least radius of variation, Rvv. Therefore, if I note down that property also, I note down that property also. Therefore, 9.7 mm. Therefore, the assuming at least it is connected by means of two bolts, right? Therefore, even the because this is discontinuous member, therefore k for discontinuous members is equal to 1. If it is continuous, then either 0.7 to 1 will come into picture, keeping in with the fixity. Therefore, the effective length of this member is equal to 2.5 meter or 2500 mm. Therefore, the slenderness ratio about VV axis is equal to 2500 divided by this 9.7. It works out, say, this lambda VV given by this formula L by R VV. Therefore, 2500 divided by that 9.4 divided by epsilon multiplied by sort of pi square multiplied by 2.5 divided by 250. It works out, say, a new value as 2.877. Similarly, lambda psi is equal to, given by this formula, is equal to B1 plus B2, both are 50 plus 50 divided by 2 multiplied by 5 divided by 1 plus square root of pi square multiplied by 2 into the power 5 divided by 250. It now works out that value as same 0.112. Even just now we have seen with two number of bolts from that previous table. I am just noting down that value. In the previous subheading also we have seen K1 is equal to 0.2, K2 is equal to 0.35 and K3 is equal to 20. Therefore, substituting all these into this formula, now I'll get this effective slenderness ratio given by this formula. Therefore, if I substitute into this formula, I am getting a new value. I am not calculating directly, showing the output now as 1.829. Therefore, now I'll calculate what is that pi value. Therefore, this, as per this class, now I'll get this pi is equal to 0.5 multiplied by 1 plus alpha multiplied by lambda I minus 0.2 plus lambda I whole square. Therefore, that value works out, say, a result as that works out, say, 2.57. Therefore, for that, now I'll interpolate from this table, right? I'll interpolate from this table 9C. Upon interpolation, now I'll get this design compressive stress. I'm not showing that interpolation now, right? Therefore, in the previous subheading I have shown that interpolation also. Therefore, FCD is equal to 51.94, right? Or like this, right? That interpolation is like this, student, right? Wherein I do have that interpolation like this, right? Therefore, for lambda is equal to some 200 and 210 from that table I have interpolated for required value of this 212, right? Like that, now you can interpolate. Therefore, upon interpolation, right, now I'm getting this result as, say, 51.94 Newton per mm square. Even now I would have this B by T and D by T, both are 50 divided by 5. Sorry, right? This will work out, say, 10, which is this is not 8, student, this is 5. Therefore, this is 10. Therefore, this is much less than 15.7. Therefore, it is non-slender. It is okay. Means you need not reduce the area. Therefore, now I can calculate the actual compression stress or design compression stress. Therefore, it now works out PD is equal to FCD multiplied by AE. But FCD just now I got that result as 51.94, that multiplied by that effective area. Effective area is equal to 479 divided by 10 to the power 3. It works out, say, a value 24.88 kilonewton. But however, my target was only 19.95 kilonewton. Therefore, it is much greater than that required demand. This is the supply. Therefore, I am able to supply this much of sectional resistance, whereas this is the demand. I am demanding 19.95, whereas I am supplying 24.88. that is how the demand and supply of in terms of the strength. Therefore, it is okay from the compression. Once this is okay from the compression, then what I'll do is I'll check for the tension. Therefore, TDG, just now we have seen, right? is given by this formula, wherein TD is equal to AG Fi divided by gamma m naught. If I do that, now I'll get this result as 108.86 kilonewton, which is much greater than 22.5. Therefore, it is okay. If it is okay, therefore it is okay in compression as well as tension, both checks. Therefore, now if I calculate the number of bolts required, this is also there in a single shear. Therefore, the bolt value for single shear, as we have seen in the previous case, as B is equal to 45.26. Therefore, the number of bolts required out of these design compression and tension governs the design 22.5 divided by that 45.26. It works out approximately 0.49 or say 2 number of bolts. Therefore, provide now either you can provide the same previous ISA 55 by 55 by 8 with the 220 mm bolts, or alternatively, if you wish to optimize, you can provide ISA 50 by 50 by 5 mm student, not 8 mm. It is not 5. It is not 8. This is 5 mm student. Please make a note. Right? This is 5 mm. Therefore, with the 220 mm bolts, 220 mm bolts. Therefore, that is how my design. That is how my design. Right? Once you understood the design, or the design is like this, right? That is how the minor sling. Let me show that minor sling student. Right? That is how my design. ISA either 55 by 55 by 8 with the 220 mm bolts here, or just now even have optimized also for your understanding as 50 by 50 by 5 mm also. Then also it is able to resist both of these minor slings. Both lengths are the same lengths, connected by means of 220 mm bolts to the one side of a gusset plate. Please see like this, right? To one side of a gusset plate using 220 mm bolts, right? 220 mm bolts like this, right? Now, that is how the design, right? Once this design is over, now I'll move to the design of the major sling, right? Now let us move quickly to the top, the last this design, the design of the major sling student, right? Yes. And then in the next subheading as design of main sling or major sling, whereas just now we have seen the design forces from this table as main sling, right? It is subjected to a maximum tension plus value, wherever that maximum is there. Yes, here 58.05 is the design tension, where I do have the negative maximum value is 64, right? In number U4M1. Therefore, that is my design compression. 64.05 is my design compression. Therefore, I am recalling both of these results and I am initiating the design. Hence, the design compression C is equal to 64.05 tension, design tension T. These are already factored values, student. Please note, these are already factored values, right? CU and TU respectively, right? Or PUs, right? T is equal to 58.05. Once again, even I can see that almost equal amount of equal magnitude of the tension and equal magnitude of the tension is there. Therefore, now I'll always design for compression and check for tension. However, you can see that almost I do have almost sufficiently, though there is a medium compression force is there and medium tension force is there. However, even the length is also not that large, right? Not large, because there is already divided into panels also like this. It is divided into 2 panels also, right? Now let me show, right? Therefore, this is a 1 panel, right? Even the second panel, right? But you please see that this main sling is part and parcel of the load transfer mechanism, because that is a truss geometry, load transfer truss geometry. Therefore, this top cord member, right? Then whatever the loads are there here, unbalanced forces will be coming to the bottom cord member through this load transfer mechanism. Therefore, this is how the loads will be transferred to the bottom cord member. Therefore, this is a major component of this truss geometry from stability point of view, right? Therefore, this will be assumed once again using 2 angles back to back. I will not assume, though there is a small force of 64 kilonewton, I will not assume this using single angle. Otherwise, that may fail in buckling in the load transfer mechanism. Therefore, now I will not take the risk like this. Therefore, I will provide 2 angles back to back. That is my assumption. Therefore, with that assumption, now what I will do is that now I will initiate the design of this major sling, right? Wherein I am designing for the compression first. I'm designing for compression, right? Therefore, now I have to have the length about this ZZ axis, that of this U4 M1 length. Both are 2.48 meters, right? Sorry, first one is 2.48 meters, student, whereas right. However, about the minor axis, is right, starting from about, let me go to this figure, right? This is 2.48, student, right? This is 2.48, this is 2.48, as well as this is 2.48 about the major axis, whereas about the minor axis, it buckles from this these bolted connections to these bolted connections, right, as one member only, like this, right? Therefore, in which case the length is double that length, 2 multiplied by this total length from this node or this joint to this joint, as one member only about minor axis, whereas about the major axis, it will buckle into 2.48, right, as two components, whereas in the minor axis it buckles about as a length, total length, as two panels, as one component only. That is how the buckling will happen about the major and minor axis. Therefore, if you understood that, then let me give the numeric values of these, right? Therefore, now I have to have the length of this major sling about the major axis of the buckling, just 2.48, right? Whereas about the minor axis, starting from the apex point to that of the at the joint at the bottom chord member. Therefore, that is how U4, that at the apex point it is U4, at the bottom it is L2 bottom chord member, right, or principal tie, it is connected at L2. Therefore, that length U4 L2 is equal to 2 multiplied by 48. So 2 multiplied by 2.48, it works out, say 4.96 is the meter, 4.96 is the length which will buckle like this about the minor axis, right? About the major axis, it buckles about 2.48 meter only, like this, right? Whereas about minor axis 4.98, like this, right? 4.98. Once I know the lengths, then what now I'll say is that here I do have this compression force is a medium force. Even the length about that major buckling axis is 2.48, whereas the buckling is critical about this minor axis. Therefore, this length is almost here and there, this 5 meter is almost large length. Therefore, I'll assume, say lambda is equal to 180 in first trial. If at all it fails, then I can reduce that slenderness ratio. Obviously, we can see that almost it will fail, right? That is how I am assuming lambda is equal to 180, but because this slenderness ratio is almost, right, length is more, therefore I advise that don't assume lambda is equal to 180. However, I do have the experience, therefore I am slowly proceeding with this. Even I am failing at one point of this checking. Therefore, as a student, you don't assume this lambda is equal to 180 now, because this length is large, even load is also sufficiently medium load. Therefore, my advice is that you assume this lambda not more than 150, Therefore, let us see how it works out. Say lambda is equal to 180. Therefore, from this table 9C, from page number 42. Let me go to that page number 42, student, right? Of IAC 800, page number 42. 42, yes, 56, yes. Therefore, for Fi is equal to 250, I do have this lambda is equal to 180, I do have 43.6. Therefore, I am noting down that design compressive stress as 43.6. Therefore, the cross sectional area required, A is equal to that, either this compression force, right? Compression force is because I am now designing for compression. Therefore, compression force is equal to 64.05 kilonewton and per 3 divided by 43.6, or say it is 1469 mm square. However, you increase this area by 25 to 50%. I advise that you increase by 50%, not less than 50%. Therefore, Now let us say if I increase by 25%, it works out same 1.25 multiplied by 1469, approximately 1836 mm square. However, since the main sling is also part and parcel of the skeleton, I am assuming two angles back to back that I already told, right, from SP61, that is Structural Engineers Handbook, SP Special Publications, Indian Standard Special Publications 6/1 1967, page number 22. Table 22, page number 102. I am trying with 2 ISA 100 by 65 by 6 with longer legs connected to the gusset plate like this. Now let me go back to this table, page number 102. Page number 102. Let me go to this 102, student, right? Yes, let me see. Yes, I am there in page number 111. Yes, 102. Yes, 102. I am there in that page number 102, student, wherein I am trying to fix I am trying to check with a section as a trial section. This is a trial section only, student, right? ISA 100 by 65 by 6. 100 by 65 by 6. Let me check, right? ISA 100 by 65 by 6. Yes, this section, right? This first row, right? Which furnishes an area of 1910 mm square. Therefore, even now I do have the radius of variation about major axis as 31.8 mm, as well as even I'm assuming the gusset plate thickness as 12 mm. Therefore, for which even now I would have, right, what is the radius of variation about the minor axis, as say if the gap between the angles is 10 mm, if the gap between the angles is 14 mm, then the radius of variation values are given. Therefore, these are respectively 2.7 and 2.85. Now I need to interpolate. Therefore, now I will do that process. Hence, I am having an area of 1910 mm square for these two angles back to back, which is just greater than 1836. But I advise that you try with 50% more, then only it will be okay, right? And the radius of variation about major axis 31.8, and about minor axis for 10 mm we have seen RYY is equal to 27 from the table, and with the thickness with the gap between these two angles 14 mm, the radius of variation RYY is equal to 28.5. Therefore, if I interpolate, now I'll get RYY is equal to 28.5 minus this difference is 28.5 minus 27 is 1.5 over a difference of 4. Therefore, over a difference of 2, it is how much? That works out at 27.75 mm. About the minor axis, about this minor axis, about the major axis it is 31.8. About this minor axis it is 27.75. Now, once I get this, even let me calculate what the effective length about the major axis. About the major axis is continuous, student. Please make a note. I have already shown, right? Therefore, assuming that partial fixity, that K value varies from 0.7 to 0.7 to 0.7 to 1. Or let me go back to this, right? How now? Let me show that, right? In the previous class, I already shown that if I go to that page number 35 of IAS attended, page number 35. Let me go to that page number 35. Yes, page number 35, right? Therefore, here I can see that the compression members in trusses, the effective length of the compression member shall be taken as 0.7 to 1 for continuous members, means K value is 0.7 to 1, 0.7 to 1. Therefore, now I am assuming partial fixity. Therefore, my effective effective length factor is equal to 0.85. Hence, for that 0.85 about the major axis multiplied by actual length 2.48 meter, or it works out at 2.108 meter, or say 2108 mm, and about effective length about the minor axis, y axis. About that minor axis, you please see that it is almost 4.96 meter length, which is about that it is only one member which is discontinuous, whereas about the major axis it is continuous because it is connected. It is split into two panels. Please see that, right? About minor axis is only one member only. About buckling about minor axis like this, right? Therefore, that is how the importance of the lengths as well as the buckling on the designs or design compressive stresses or from buckling point of view, right? Therefore, if you understood that, therefore Ly is equal to 1 because it is discontinuous, 1 only multiplied by Ly. Ly is equal to 4.96, or it is a 4976 4976 mm. Therefore, the actual slenderness ratio about the major axis lambda z is equal to Lz divided by Rzz. It now works out say 2108 divided by 31.8 or say 66.29. However, similarly about the slenderness actual slenderness ratio about minor axis lambda y is equal to Lyy divided by Ryy, which is equal to 49.6 divided by 27.75 or 178.74. However, if I go to this table 3, page number 20, let me go to that page number 20, student, page number 20, yes, and then in page number 20, wherein this indicates the maximum values of the effective slenderness ratio. However, these loads are inclusive that of the wind and earthquake. Therefore, a member subjected to compression forces resulting from combination of the wind and earthquake, this serial number 3, for which the maximum slenderness ratio is equal to 250. Therefore, I have just noted down this from table 3 of IS 800 2007. IS 800 2007. Therefore, this slenderness ratio, what now I got about the minor axis is 178.7, which is less than 250. Therefore, it is okay. Once it is okay, then what I'll do is I'll go to same table 9C, page number 42. Then I'll interpolate. Just now I've shown that lambda is equal to 170. I do have FCD is equal to 48.1. For lambda is equal to 180. It is 43.6. This 43.6 I already shown, right? Therefore, if I interpolate, I'll get for 178.74. It is how much, right? Therefore, this design compressive stress is 48.1 minus 48.1 minus 43.6 divided by over a difference of 10 or a difference of 8.74. It is how much? That works out say 44.167 Newton per mm square. Even from this table 2, page number 18 as well as page number 19, just now discussed in the previous subheading also, right? Now I have to have the B, outstanding leg, is 65 and connected leg, because the longer leg 100 mm is connected to the gusset plate 100 mm. Therefore, D is equal to 100 mm and the thickness is equal to 6 mm. Therefore, these ratios B by T is equal to 65 by 6 is at 10.83, which is less than 16.5. Therefore, it is not slender. Even D by T is 100 by 6. It is 16.67. This is greater than 15.7. It is not okay. It is not okay means you need to either restrict, either you increase the thickness, right? Thickness and make it not slender. Therefore, it is greater than 15. It is greater than 15.5. Means it is a slender section. Either you reduce the area so as to calculate the compression force, or you increase the thickness of this angle, either of the two is true. That's why I told that don't proceed with this lambda is equal to 180, right? Even don't proceed with this lambda is equal to 180. I already warned, right? Even I have given second warning also that don't proceed with this 25% area. I asked you to proceed with 50% area. Therefore, now we are almost, right, facing a problem now. Now, nevertheless, I'll make a small correction so that I'll get out of this problem, right? How? Now I'll show, right? Therefore, now I have to have this individual check itself is not matching. It is not okay. Therefore, individual check also it is the slender section. Even now, what I'll do is that in such a case, you restrict this D by T to 15. There is no other option. Therefore, either you say that D is equal to 15 multiplied by T, right? Therefore, that connected leg should be restricted to 90 mm only, right? Even if the connected leg is 100, what you can assume is that out of that 100 mm, 10 mm is ineffective. Only 90 mm is effective, right? That is what, right? Restricted to 90 mm. And also check, even other check, whether is it okay in B plus D divided by T, right? B is 100 and D is equal to D is equal to 100 plus 65, 165 divided by 6. Even this is 25.8, which is greater than 25. Even here also it is not okay. Therefore, it is not okay. Therefore, means if I go to this page number 18, let me go to that page number 18, student, right, of IAS 800. Let me revisit that page number 18. Just bear for a moment, right? Therefore, for this double angle, right, for this double angle, right? You please see that these, right, single angle and double angles, with components are separated, right? There even I do have b by t greater than 15, d by t greater than 15.7, and b plus d is also greater than 25. That indicates that the section is not semi-compact. It is greater than 15.7 means the section is a slender section, for which a part of that area is ineffective. Therefore, now I'll calculate how much of area is ineffective. Either you do like that, or you restrict. Either you increase the thickness of this section, and one option, alternative, what you can do is either you increase the thickness of this double angle section, or you restrict these legs, right? These either two legs or one leg, so that it is okay in this check. However, here the longer leg you can restrict it to 90. Then you can choose another section as appropriate, right? However, what now I'll do is I'll try to continue with the same section, but I'll try to reduce the area, right? Reduce the area, right? Hence, what now I'll do is I'm not changing the section. Therefore, I'm assuming that instead of that 100 mm, only 90 mm is effective. 90 mm is effective. Therefore, what is the effective area? Is nothing but the total gross area. However, the gross area is equal to, from that table 1910. How much is ineffective now out of this 100 mm? Is that I am restricting. The code says that you restrict it to this D, not more than 90 mm. Means out of that 100 mm, right? 10 mm is ineffective. Therefore, now I am deducting that 10 multiplied by 6. I am deducting. Therefore, 60 mm. If I deduct, now it works out, say 1850 mm square only. Therefore, I am taking that 1850 mm square, that multiplied by now 1850, right? 1850 multiplied by 44.167. Now it works out 81.7. Therefore, the design compression force is 81.67. However, the compression, we are designing for a compression force of 64.05 kilonewton. Therefore, it is okay. Means if I just reduce this ineffective area, this can able to carry. Therefore, it is okay. This is okay, right? Once it is okay, whatever assumed section is okay. Therefore, by restriction, right, I am assuming that I have reduced that length by 10 mm. Therefore, it is okay, right? Hence, this is my final section. Means it is okay in compression. Similarly, now if I calculate in tension, if it is carrying this much of tension, then that is my final section of 58.05. Therefore, either you do like this, or alternatively, let us say you don't want to proceed with this, right? Then what you can do is that even this is the second alternative, student, right? Though I am okay, even you can do this second alternative, because this B plus D is greater than 25. What you can do is you can increase the section from that previous ISA to ISA 100 by 65 by 6 to 8 mm. Therefore, I am choosing with a higher thickness from 6 mm to 8 mm. Then what happens? Now let me check. Which furnishes an area of 2514 mm square. Therefore, now B by T is 65. The same outstanding leg is there, but the thickness, now you can see in this figure that thickness is equal to 8 mm instead of 6 mm. Therefore, it is now this ratio is working out 8.125, which is less than 15.7. It is okay. However, this D is equal to 100 by 8. 12.5, it is less than 15.7, means that is semi-compact section. Therefore, by increasing the thickness from 6 mm to 8 mm, instead of that section as a slender section has become a semi-compact section. That is how we can make correction to the designs if at all they are failing, right? Therefore, that is okay. Now let me check this check also, right? B plus D is now 100 plus 65, 165 divided by thickness is now 8 mm. Therefore, it is now 20.63, which is less than 25. Therefore, it is okay. Means there is no problem. Even there is no buckling. First of all, there is no buckling of this 2 ISA 100 by 65 by 8 section. Whereas at least that previous section 2 ISA 100 by 65 by 6 was buckling, and we have reduced the ineffective area, right? Even you can proceed with that, even still it is able to carry a load of 81.7 kilonewton, no problem, right? Or otherwise, if you don't want to proceed, what you can choose is a higher section with this much of thickness, 8 mm. Therefore, it is not at all buckling. Then that is a 2 ISA 100 by 65 by 8 as I have shown here, right? Therefore, now, however, I already designed this as a principal tie, right? Wherein now let me go to that principal tie. There I already designed. Let me show that, right? I am going back to the principal tie AS. This is where that principal tie was subjected to a compression force of 148.5 and a a tension force of 148.5 and compression force of 75.6. However, here I am targeting roughly some 65 kilonewton. Here and there it is same. Therefore, there I have provided the same section, 2 ISA 65 by 100 by 65 by 8, connected to one side of a gusset plate, 12 mm thick, like this, 12 mm thick. There I have shown that this section could able to carry, right? This section was able to carry a design compressive stress, because there I have already checked design for compression. This section can able to carry, right, design compressive strength of 82.1 kilonewton, right? Therefore, that is how the section carrying capacity, right? Section carrying capacity, design compressive strength, right? Therefore, I am just recalling that. Or what I can do alternatively is that even I am showing the results, right? Therefore, what is my lambda z now, right? Slenderness ratio about the major axis is LZ divided by RZZ is 2108. That previous result divided by RZZ is equal to 31.6. It works out as 66.7. Whereas there is a small change now, right? Even slenderness ratio about minor axis is 4960 divided by 28.25, because these are the modified radius of gyration about the major axis 31.6 and about minor axis 28.5. Therefore, that now works out about minor axis. The slenderness ratio is 175.58. Therefore, now I'll once again interpolate like this. Therefore, for lambda is equal to 170, lambda is equal to 180, FCDR 48.1 and 43.6 respectively. Therefore, if I interpolate, now I'll get a design compressive stress. Upon this interpolation, I'll get this result as approximately 45.89 Newton per mm square. Therefore, for this section, 2 ISA 100 by 65 by 8 with this modified section, the design compressive strength PD is equal to AE multiplied by FCD 2514 multiplied by 4559, because this area is 4559. That is the area, right? That divided by 10 to power 3. Therefore, it can resist up to 114.61 kilonewton. However, it is just subjected to a compression force of a mere value of, right, a small value of 64.05 kilonewton only. Therefore, it is okay in compression criteria, right? Whereas if I check for tension, however, the design tensile strength, we have already seen in the previous subheading that under the yielding of the gross cross section TDG is equal to, given by this formula, AG, right? This value, right? AG Fi divided by gamma m naught, where AG, now I know this value, AG is equal to 2514 multiplied by Fi, 250 divided by 1.1 it works out same a value 571.36 kilonewton. Even when in the net section rupture as well as the shear criteria, assuming 20% reduction, I'll get 0.8 multiplied by 571.36. it works out approximately 457 kilonewton, which is much greater than just 58 kilonewton tension only. Therefore, I am not taking for exact calculation because the tension design tension force is very small, whereas in cross section, yielding of the cross section itself is almost more than 12 times more. Therefore, I am not going for the exact calculation. If you want, you can do the exact calculation also, as I explained in the previous subheading, or even you may refer back to our video on the design of tension members elaborately. Right? Therefore, it is okay in tension also. Hence, this is my final section. Or say 2 ISA 100 by 65 by 8. Connecting. Right? This is my final section. Now, next subheading is, if it is okay, then what are the bolted connections? Just now we have seen in the previous subheading that because two angles are connected back to back, right? Therefore, these are a double shear. Therefore, the bolts are in double shear. Hence, for the double shear, now I can say, sorry, just wait for a moment, right? This is in double shear. Hence, for that, sorry, not this one, right? This is a double shear. Hence, for double shear, I have the design strength of these bolts in double shear. VDSB is equal to 90.52, even KB worked out 0.5. Therefore, the design strength of the bolt in bearing is equal to this is 96 kilonewton out of these two, which was minimum 90.52 kilonewton. Therefore, once I know that bolt value is 90.52 student, now what I am doing is number of bolts required out of these two, compression and tension. Let us see this, right? A compression force of just 64 kilonewton, which is greater than tension. Therefore, I design for a compression force of 64 kilonewton divided by 90.52. However, I require 0.7 only, but let us provide two 20 mm dia bolts. That is my final section. It's a cross section. Provide two ISA 100 by 65 by 8 with the two 20 mm dia bolts, or alternatively even you can provide two ISA 100 by 65 by 6. Even that is also able to carry a force of 81.7 kilonewton, which is much greater than 64 kilonewton. Either of the two is true, no problem, right? Hence, that final section of this main sling is like this, right? That's a cross section, student. This is my final section, right? That is how my main sling consists of two angles back to back, either the two ISA 100 by 65 by 8 connected by means of at least two bolts here. To one side of two sides of a gazette plate, like said, two bolts here, even here also two bolts will be there. That is the design of the main sling. Student. I hope you enjoyed the discussion what we had in today's class. Therefore, don't forget to click like, share, subscribe, and turn on all the notifications to our YouTube channel. We'll meet in the next class. The design of roof trusses. We will try to design these purlins as well as the bracings to the rafters. Till then, bye bye, students.